In this video, we are going to cover the proof for the unbiasedness of the slope estimator in the multiple linear regression. So I'm going to start from the definition of beta 1 that comes from the partialing out interpretation. So look at the previous video if you don't know where it comes from. Beta 1 hat equals the sum of the product between yi and ri1 hat over the sum of ri1 square. And what is this ri1 hat square? It's just the residual of the regression of xi1 over the other xi. So xi2, if you have xi3, you add plus alpha 3 hat xi3, etc., etc. So ri1 hat is just xi1 minus the predicted value of xi1 that's coming from this regression here. So first we're going to cover some important things, nodes, and they all come from the fact that ri1 hat is a residual from a simple linear regression. So the first thing is that the sum of ri1 hat, this is a sum of residuals, it should be 0 from the first order condition for alpha 0 in the simple linear regression model. Then sum of ri1 hat times xi2. So xi2 is a regressor, and the sum of the product of the regressor times the residual should be 0 from the first order condition for alpha 2, so I'll call it FOC2. And I need to find, although, because it will be useful for later, what is the sum of the product of ri1 hat times xi1. So xi1 is not a regressor here, it's a dependent variable, so it's where we have y usually. And I'm going to expand this. So this is equal to the sum of ri1 hat times, and xi1 is just, let me come back a little, alpha 0 hat plus alpha 2 hat xi2 plus ri1 hat. So I'm just taking the equation at the top here and plugging this in this equation. I get this. So I'm going to distribute the ri1, and I get sum of ri1 alpha 0 hat plus ri1 hat alpha 2 hat xi2 plus ri1 hat square. All of this is in the sum. Then I'm going to break this sum, so I have sum of ri1 hat alpha 0 hat plus sum of ri1 hat alpha hat xi2 plus the sum of ri1 hat square. We can see here that alpha 0 hat and alpha 2 hat are constant, so I can take them out of the sum. So I have alpha 0 hat sum of ri1 hat plus alpha 2 hat sum of xi2 ri1 hat plus the sum of the ri1 hat square. And remember, we say that the sum of ri1 is 0 because it's a sum of residuals. So this is 0. And also the sum of the product between ri1 hat and xi2, which is here, is 0. So in the end, we just have ri1 hat square. I'm going to rewrite this like this. Sum of xi1 ri1 hat is equal to this. Now we have the tools we need to go over the proof. So to show that the expectation of beta 1 hat is equal to beta 1, which means it is unbiased, we just need expectation of beta 1 hat conditional on x, so this is the conditional expectation, is equal to beta 1. Because this implies that the unconditional expectation is equal to beta 1 from the law of iterated expectation. There is a video about the LIE, so just look for it if you don't remember how it works. So I'm going to focus on expectation of beta 1 hat conditional on x. And we know that the expectation of sum of yi ri1 hat over sum of ri1 hat square conditional on x. I'm going to expand the y. So I get expectation of the sum of ri1 hat times, and y is equal to beta 0 plus beta 1 xi1 plus beta 2 xi2 plus ui. So we are here in a multiple linear regression model where we have just two explanatory variables, but the logic is the same if we have more x's. So if we have xi3, xi4, etc. So I'm just putting at the bottom the sum of the ri1 squares. Everything is conditional on x. So let me just write a side note here. It's about the ri1 square. And just ri1 here, it's just xi1 minus xi1 hat. So this is equal to xi1 minus alpha 0 hat minus alpha 2 hat xi2. And alpha 0 hat is x1 bar minus alpha 2 hat x2 bar. And alpha 1 hat is just the formula of the slope estimator in a simple linear regression. So xi1 times xi2 minus x2 bar over the sum of xi1 minus xi2 minus xi2 bar square. So as you see here, alpha 1 and alpha 0 just depends on x's, no u, no y. And ri1, it's sum of some things that just depends on xi's. So xi1, alpha 0 depend on xi1 and xi2. Alpha 2, let me correct this, alpha 2 also depends on xi1, xi2, and then we have x2 bar. So here, ri1 is a function of x, x1, and x2. So in the expectation here, because it's conditional on x, the bottom part here just depends on x, I can get it out. So now I have 1 over the sum of ri1 hat square times, and then what's left inside, I'm going to distribute the ri1 hat over all the terms. So I have sum of beta 0 ri1 hat plus, I'm going to break the sum of ri1 hat, so beta 1 ri1 hat xi 1 plus the sum of beta 2 ri1 hat xi2 plus the sum of ri1 hat ui conditional on x, close the expectation. So I'm going to get some of the betas out here. So here we still have in front the sum of the ri1 square. Then I have expectation of beta 0 is a constant. I get it out of the sum of ri1 hat. Then beta 1 is a constant. Beta 1 times the sum of ri1 hat xi1. Beta 2 is a constant. Sum of beta 2 ri1, times the sum of ri1 hat xi2 plus, and here there is no constant, so ri1 hat ui conditional on x. So we have some results. Let's say that sum of a residual is 0, so this term will disappear. Sum of ri1 times xi1, if you remember, we have a result here at the top that says that this is the sum of the residual squared. So this is the sum of ri1 hat square. Then here ri1 is a residual and xi2 is a regressor in the regression of xi1 over xi2. This is 0, so this disappears. And in the end we have the sum of r1 hat times ui. Let me rewrite this. We have we have 1 over the sum of ri1 hat square. This disappeared, so now we just have expectation of beta 1 sum of ri1 hat square plus the sum of ri1 hat ui conditional on x. So I'm going to get the beta 1 sum of ri1 square out of the expectation, because this ri1 is just conditional on the x. Like if it's conditional on the x, it's like a constant. I can get it out. So I get beta 1 times sum of ri1 hat square over sum of ri1 hat square. This is 1, so I can get rid of it, plus the expectation of the sum, and we know that the expectation of a sum is the sum of the expectations. So this is a sum of expected ri1 hat ui conditional on x. ri1 being just dependent on the x's, I can get it out of the expectation. So I get beta 1 plus the sum of ri1 hat expectation of ui conditional on x. This is equal to 0 according to Gauss-Markov assumption 4, MLR 4. And if this expectation is 0, the product of 0 with ri is 0. Then we have a sum of zeros. And I forgot to put here 1 over sum of ri squares. So 0 divided by anything is 0. So we just have beta 1. Let me write the result. Expectation of beta 1 hat conditional on x is equal to beta 1. Then by the law of iterated expectation, expectation of beta 1 hat is equal to beta 1. It's unbiased.